Hello everyone, my name is Kanchan. I'm a postdoctoral researcher at Syracuse University. First of all, I would like to thank the organizers for giving me an opportunity to discuss my research work. In this talk, I'll discuss some of the key challenges that from research side we face when we look for very long duration signals in the data. So the title of the talk is Hierarchical Searches for Subsolar Mass Binaries and how this method can be used for in third generation detector era as well. Okay, so as you can see, gravitational waves can be emitted from different sources and they can be seen at different frequency bands. But currently what we are observing is a very narrow band and from the terrestrial interferometers like LIGO and Virgo, we are only able to find these waves from compact binary images. Until now, there are more than 90 sources that have been cataloged in various papers. And these catalogs have some of the exceptional events coming from binary neutron star merger, neutron star black hole merger, and also there is an evidence for intermediate mass black hole. Ongoing run is fourth run, and so far, I mean, there are already hundreds of significant gravitational events that have been put out on Grace TV. There's also one interesting event, which is GW230529. This is interesting because one of the component masses fall in the mass gap. So technically, we don't have mass gap anymore. So far, what we have seen is the gravitational wave sources that have compact objects mass above 1 solar. But there is no harm in asking if there are sources that may have masses less than a solar mass. Now, these are interesting sources because they don't follow the mainstream channel of stellar evolution. They are mostly hypothesized to form in the early universe. And if suppose these sources exist and they form binaries, the emitted gravitational waves can be detected in ground-based detectors. Now, since these are very small, they spend quite a lot of time in spiral stage, and that's why their signal are quite long in duration. So because they are longer signals, match filtering is one of the sensitive method that can be used for searching these kind of sources. Now, there have been previously attempts made to look for these kind of sources in LIGO data, but all of these searches, they faced one of the bottleneck, which was heavy computation demand, just because the parameter space was quite large, and also the signal duration it seemed to be like quite a bit too much. So just to give a fair idea, if we assume that match filtering is basically performing FFTs, then FFT operations scales as n log n. If we have more number of templates, then these number of operations keep on increasing. What is going to happen in 3G era will be having more detection, basically one signal per minute. And in this sensitivity band of like Cosmic Explorer and ICENT telescope, the signal will spend a few minutes to hours, making it difficult to use the current technology for detecting these kind of sources. So ultimately, we need to speed up the process and we need faster match filtering based search pipelines. So one of the ways in which match filtering process can be speed up is by performing the entire search in multiple stages. So how do we do this? Suppose we have here a grid which shows the parameter space which we want to explore. And somewhere here, there is a signal line. What we do is first we try to search the signal in a coarsely sampled data with a bank that is sparse in nature. Now, by sparse, I mean that the templates are further apart. And this basically speeds up entire process of scanning the entire parameter space. So once we have identified the potential candidate from this step, we try to follow up in these candidates in the next stage by performing a more finer search around the parameter space of the detected candidate. So in this second stage, we sort of compensate the SNR loss due to the sampling rate and other things by performing match filtering of the data segment at high sampling rate and with less number of templates. Now, effectively, what we are doing in these two stages, we are reducing the number of templates that can be used to get to the final signal. And if we look at the previous result, if we compare the results from the old paper, the speed basically comes out to the order of 20. If we follow all the triggers, zero lag triggers in the next stage. Now, if we also account for the noise, then the speed can go a little bit lower, but this is also like quite significant if we compare any other search pipelines. So this method can directly be used to look for signals from subsolar mass compact objects. Just to motivate the audience, I would like to just compare the results of how the LVK searches are currently using the PyCPC searches and what we are trying to do. So Maggie et al., they have already shown that the fractional SNR loss, it basically increases with the lower frequency cutoff, which we use to perform the match filtering. Now, if we perform the search at 45 Hertz, static frequency of 45 Hertz, then we basically end up getting 8 to 9% of SNR loss. This naively saying that it scales to volumetric loss of 24%. Let's say that we don't want to perform at 45, we reduce the lower frequency cutoff from 45 to 35. Then we see that the SNR loss is somewhere around 3%. Okay. So this is good. So we use this sort of strategy to perform hierarchical search. We constructed bands at 35 Hertz. This basically increase the number of templates, but that's okay because our core search is faster. So here I show how the templates are placed in the course bank, and each grid in this particular plot on the right-hand side, it shows that how many templates would be there inside the neighborhood of each course template. So suppose if there is a signal lying somewhere in this parameter space, and we try to follow up in the next stage, we only have to use a couple of hundreds template to make a detection. All right, so we took 7 days of data from O3 and we ran hierarchical search over this particular data. We couldn't find anything. But if you see that the strategy works fine because we have a sort of a similar profile what we get in the flat search. So here flat, I mean the standard PyCPC search, and the hierarchical search, it mostly looks same. And the foregrounds, if we try to compare, we don't have any significant, but most of the foreground triggers lay over the ones which are obtained from the flat search. So the next thing is to ask, are we gaining any sensitivity? For that comparison, we compute volume time sensitivity. And for this, we did fiducial injections in our data. And we computed this quantity for the flat search and also hierarchical search. What we found that for each frequency, for each chirp mass and IFR bin, we have a volumetric improvement of the factor of like 1.1 to 1.2. Now, this is kind of good because if we have like certain models, like dark matter models, which we can use to constrain the which we can use to constrain from these estimates, then having a volumetric improvement of 10 to 15% can actually give a better estimate of the fraction of primordial black holes existing in the universe. So I will leave the summary slide over here. I would just like to highlight that hierarchical search strategies can be easily used for performing expensive searches. Previously, it has been shown that it is fast, but then, of course, these methods can be directly implemented for the low mass binaries. And in this work, we showed that just by decreasing the low frequency cutoff from 45 to 35, we get a 6% FNR gain, which is approximately 10 to 15% of volumetric improvement. And this can help in constraining the fraction of dark matter. Thank you.
Thank you. Any questions?
Hi, thanks for the great. So I just needed clarification. So where the number of 35 hertz and 45 hertz is coming from?
So, so this is just the starting frequency which we use to perform match filtering. So the currently what LIGO and other papers are using is bound at like 45 hertz. So basically, match filter starts at 45 hertz, even though the sensitivity is quite good around 15, but still because of the heavy computation demand, this is sort of pushed to higher value. So you can see that if you have higher cutoff at the lower frequency, then the percentage less SNR loss is quite high. So we are just testing, like if we suppose bring it down to some value, how much improvement we can get.
And if you go a bit lower, then it improves.
Yeah, we can do that, but as you can see, it mostly flattens after like 20. So
Thank you.
Again, very nice talk, thank you for it. And so on the same topic, perhaps I know, but when you're doing searches for please go on please more. But I was under the impression that usually the templates when everything starts at around 10 megahertz in the usual searches for physical heavier slower messes, and not in 35. So perhaps and I expect that as you go to lower messes, they will have more SNR in the lower frequencies. So those two things do not seem to be a first improvement. I found that how it's not even pushing. I would expect it to be 10 hertz, for example, not 30 or 40.
right, but if you look at the sensitivity curve of let's say O3 over here, there's not much to gain at least at 10 hertz. So usually the CBC searches or the general binary black hole to neutron star searches are conducted at like 15 hertz and above. But because this is subsolar and the signal length can actually be like, quite a bit. So just to compensate the computation demand, we can actually push the low frequency limit to a bit high value. Does that answer the question?
Yes, so just telling you that we follow my search. Yeah.
Okay.
So I have a question.
Yes.
I have no astrophysical prior knowledge of the spin distributions for these subsolar mass dark matter objects. What kind of spin distributions do you assume? What are you sensitive to?
Right. So, well, in this particular work, we try to keep the spins to be free parameter ranging from -9 to 9. We haven't used any particular model that would describe dark matter distribution or anything. This is just a blind study we try to do. So, but then also given the chirp mass which we are trying to put, because we are expecting one of the components in the binary to be in the subsolar mass range, the other can be anything. So the chirp mass is like in log scale, it is around 0.2. So,
and it's an aligned
spin, yes. Yeah.
Any more questions?
Thanks for the next talk. So I don't have a good intuition for the low masses, but for high masses, like if you do a similar thing, you might get to a wrong region of the parameter space in the core template band when you, as in compared to like if you have a finite template band. So do you worry about that? Like the 45 hertz, if you increase the 45 hertz threshold, would you worry about that?
So this constraint is actually this lower limit constraint which we are choosing. This is specific to subsolar mass searches. If we are talking about a generic high mass system, we don't keep the 45 hertz. We always use the lower frequency, like which could be like 15 or 16, I don't know. So because the number of cycles are very less, so we don't want to lose SNR in those cases. This particular strategy is for subsolar mass binaries.
Thanks.
Any more questions? Oh, let's thank our speaker again.